Now we go into chapter 5, and at first we can go quite quickly because of the order. We have already talked about Fourier series and Fourier transform. So you can say that these are just special cases of the function space or the vector space that we have. Basically, you have function that expand in basis. In Fourier series, the bases are the sine and cosine or the exponential function equivalently. And those are Fourier series are the discrete case of the expansion, and Fourier transform is just basically the continuum limit. Basically, you expand something in a continuum. The basis now is instead of discrete becomes continuum, and it's essentially very similar. And the textbook mostly will deal with discrete expansion, but it's the same. If you go to the continuum limit, you get similar result. So at first something would be very similar, so we'll go very quickly. So and I'll skip a lot of this description because you can read them yourself. Basically, a function space you can either define using a few of these basis functions to so-called span your space to even a finite number of basis function and create a space based on these functions, linear combination of these basis function. And that is you can define a vector space that way, but most likely we'll deal with just a general space and then a general basis set of basis functions, just like the sine or cosine. In that case, the number of basis functions can be infinite number. Like Fourier series, you have infinite many basis functions, so that is fine also. And we'll deal with this function space. Most likely was restricted to so-called Hilbert space. And the textbook has listed a few of these properties. So like the usual multiplication and addition and all those usual way of doing that kind of algebra exactly the same. The main difference is that the two main points, like Hilbert space, those spaces will form a complete set, and that mathematicians prove this kind of thing. Oh, okay, and like Fourier series, Fourier transform, they already proved those complete set. Complete set means the basis. Any function in the space can be expressed as a linear combination of the basis function. So that proven and generalized to other general Hilbert space. If you find a basis function, then that is also a complete set. And also, the important thing is in Hilbert space, you can define the inner product or scalar product, right? There are different ways of defining a scalar product. One common way is integral. It's not the only way, but we'll deal with it most of the time. And you can use that as the illustration of the property of the scalar product, because the scalar product also has some property that it needs to satisfy. So for this special case of defining a scalar product by integral, so you define a function. In this case, it's a function of one variable, and you can restrict your domain also. So from A to B, you have f and G2 function. The scalar product is defined as a complex conjugate of f multiplied by G, and they are a function of S. And also you can multiply by weight function Ws and integrate that. One requirement for scalar product is that if you have this scalar product or function with itself, we require to be positive and real and positive. So it's real and greater or equals to 0 and real. Obviously, if it's not real, of course, we cannot talk about whether it's greater or less than 0. Okay, so we require that. And it's 0 when f is exactly 0, otherwise it's not 0. Okay, and then because of that, then there's a restriction on the weight that you can use the weight WS. Obviously, must be real and greater or equals to 0. Don't use actual 0 because 0 that doesn't make sense. So, or I can say it can be 0 at the isolated point. That's fine, but not identically 0. It's a definition. It's just a general expression that you can define a scalar product with a weight. And later on, we'll have some case that has a specific form of the weight. And so it's just that you can define your scalar product with a weight also. Right? It doesn't have to be just the product of two functions. Okay, and that's just a more general situation. And also require that the scalar product is obviously linear to F and G. So you can say multiply by, say, F times alpha G. That becomes alpha Fg. In that case, obviously, multiplied by alpha. It's scale. It's not a function. It's just a number. Multiplied by alpha here, you can take the alpha out. So that's obvious. If you can have like multiple alpha in F, then you see that it's you have a complex conjugate out, right? Okay, and another property is that if you reverse the order G and F, then it's like Fg and take the complex conjugate, right? You can see that from the definition, if you call F and G, F equals to G and G equals to F, just reverse this and just basically just putting the complex conjugate to G instead of F, then it's the same as taking a complex conjugate of the whole thing. Because when you take the complex conjugate of the whole thing, you just basically that change back to F and G change the G complex conjugate, right? And W is assumed to be real, so it doesn't change. It's okay. So this is another property of the scalar product. Okay, so these are just property of the inner scalar product that associate with the Hilbert space. And by this property, then there are the most important thing that you can now define your basis function, but also you can define your there's an inequality which is quite straightforward. So because with the scalar product, you can see it right away. The Schwarz inequality. I think I mentioned that I actually use it when we talked about the uncertainty principle. And I mean, the whole thing is so that we analyze this function space like what we analyze a vector in the usual geometrical space. But except that now these are functions, not the vector in the geometrical vector. And then it can have many dimensions, have a large number of dimension, finite number, or infinite dimension. So, but otherwise, you can use many of these what you obtained in property of vector space, and then translate that to this function space, right? So this Schwarz inequality is just like that. So basically, it's saying that in usual vector, you have this two vector A dot B, right? Obviously, A dot B is by our definition of dot product is A by A cosine theta. Theta is the angle between them, right? If you square them, This square, this is square, this is square. Cosine square theta is less than 1, so less than square b squared. Right. So that is trivial, right? And the usual vector in geometrical space is this Schwarz inequality is quite straightforward. Now in function space, basically using this scalar product, we define the form is exactly the same. It's just this dot product becomes your scalar product. So G. Now, except that this is not necessarily real, so you need to take the complex magnitude square, and likewise, it's smaller than the f this ff square dt. Okay, and they are by definition they are real. The product of these two that are like the magnitude A, magnitude square of A and magnitude square of B. That's greater than this one. And the proof is quite straightforward. Basically, you consider this vector instead of just f and g. You consider this vector f, to itself. This is f minus this lambda is this g f divided by g multiplied by g. So this in itself is a vector, right? And then with itself. Obviously, this one is, by this definition, is greater or equal to 0, right? And you know what I'm doing, right? So just basically consider this vector and the scalar product with itself, right? And then you use the property of the algebra of the scalar product and to expand it in terms of your f. Right? And then this one to this one, and then this one to this one. And so you have plus this, when you put in the formula of scalar product, so this one multiply the complex conjugate of this one, so it's complex conjugate square. F divided by GG square. And GG are real. I mean, this is by definition real. Right. And then this and that, G. Right. And then they are constant, this and that. So minus right, and then this and that is minus that's conjugate, and then this and that is G. Oh. Okay, now we do cancellation or simplification. This one cancel with one factor here. And then use this property. This is GF, is this FG complex conjugate. So this two combine to just magnitude square. And FG, the complex magnitude square, is just GF is just FG complex magnitude square, right? Because of this property. So it doesn't matter which one is in which slot, you can interchange them. And likewise, this one, you can show that this is an FG and this is FG complex conjugate. So altogether is also FG square. So altogether you have these three terms are the same, and you have two of these are negative, one of these are positive. This is negative. model, right? And we already show that this is a scalar part or vector with itself, so it's going to see, right? And we rearrange the order, multiply this to the other side, you get this one. Oh, there's no square. I copy. There's no square because it's already square. Yeah. This one is good. Okay.